Hello?
Yeah.
Okay, yeah, sorry, I had to find my pen. Okay, so what this Dirac delta function, like, so for example, in one dimension, so the Dirac delta function, we would represent it like this. This is the Dirac delta function. So in 1D, this would be defined as 0 if x does not equal to 0, and would equal infinity if x equals 0. So in other words, only at x equals 0 it would blow up, so it would go all the way to infinity here. Okay, and then all of a sudden, as soon as x does not equal 0, it would just go flat on the x-axis. Okay, so this in red would be the Dirac delta function in one dimension, such that this all happens such that the integral from minus infinity, because this is going all the way to minus infinity, all the way to plus infinity, the integral from minus infinity to plus infinity of the function dx, meaning the area under the graph, meaning the area that I'm trying to represent here, if I can just somehow shade it, is actually equal 1.
Okay.
So that's what the Dirac delta function is. I mean, it's not really a function because it's not defined at x equals 0.
Right.
But I mean, for some reason they call it the generalized function in mathematics.
I'm assuming if it were,
Right?
yeah, and I assume if it were in more than one dimension, you'd actually have some.
Yeah. So some of the useful properties that we could use with this is, suppose that f of x is continuous. Right? So if f of x is continuous, then that means f of x times the Dirac delta function has to equal to, so this would be 0 everywhere except where x equals 0. So where x equals 0, this would pick up whatever value of the function f at x equals 0, right, times the Dirac delta function. So this is sort of what we're saying. So this is because everywhere else other than x equals 0, this guy will vanish. Right? So if I were to expand this a little bit more, I could say that the integral from minus infinity to plus infinity of f of x delta x dx, that has to equal to, so it's 0 everywhere except where x equals 0. In that case, this would be f of 0, and it would be a constant, so I can pull it outside the integral, and times the integral from minus infinity to plus infinity of the Dirac delta function dx, which we just said it's just 1. This guy is 1. And so we end up with f of 0. So the answer for this integral would actually be f of 0. So under the integral, the function, or the delta function, picks out the value of f of x where x equals 0. And then it would just trash everything else or zero out everything else, right? Now the other component of this, I could change the domain of the Dirac delta function. So I could go a little bit to the right of it, a little bit to the left of it. In other words, what I could say, I could say the Dirac delta function, and now instead of x, I will call this x equals a, and just like I made the first argument, this would equal 0 everywhere where x does not equal a. In other words, everywhere where this is not 0. and it would equal infinity if x equals a. So it's just a way of shifting the Dirac delta function to the right with an amount a. So with that said, now we can say that the integral from minus infinity to plus infinity of the Dirac delta function of x minus a dx will equal to 1. Okay, and so the equation, this equation here, then would become, under this argument, I could also shift this equation and modify it. So I could say that f of x times the Dirac delta function shifted by an amount a. Now it will pick up the value, but instead of picking the value at x equals 0, it'll pick the value of f at x equals a times the Dirac delta function x minus a, so that the integral becomes from minus infinity to plus infinity of f of x delta x minus a dx. And now what do you expect the answer to be? Well, it's just going to be f of a. Pick up the value of the function at a. Dirac delta function of x minus a dx, the integral of that is 1. So we will just end up with f of a, and everything else will go to 0. Right?
And if it were,
so yeah, so like a solid example on that, right? Let's say I integrate from 1 to 4, right? X to the 4, Dirac delta function of x minus 3, right? So this will be 0 dx. So according to what we just said, oops, where's the pad? Maybe open the pad. According to what we just said, this will pick up the value dx. This will pick up the value of f of x. And who's f of x here? Clearly f of x is x to the 4. Right?
Yeah.
So this will pick up the value at where x minus 3 is equal to 0. So this will just be f of 3. And everything else will be 0. So this will be 3 to the 4, which will be 81. Of course, assuming that f of x is continuous between 1 and 4, which it is, because x to the 4 is a polynomial, and therefore it's continuous on all real numbers. Okay. Now,
team viewer shut off.
It did. You could reconnect. Now, of course, I can generalize this Dirac delta function into 3D.
Is it the same?
Yeah. So in 3D, we define it as like this, meaning 3D
Password?
as a function of r. It's the same password I sent you initially. It's
4745.
let me see. I forgot. 4754. Yeah. So this will just be x delta y delta z, such that if I were to integrate this over all space, you will see integrals like this in electrodynamics. So an example on that would be the work in an electrostatics over the work will equal to the integral of the electric field squared d tau over all space. We'll come to this in chapter 4. Okay, so this is f or if we were to integrate this d tau over all space, right? So this is actually made up of 3 integrals, and each one of them is expanding from minus infinity to plus infinity. So this is a triple integral, right? Delta x, delta y, delta z, dx, dy, dz. And what do you expect the answer will be? 1. 1. Yeah, so it's just a volume integral of 1. Now, I can generalize what I wrote at the beginning when I said right here. I can generalize this result in 3D, and I could say, let me write it. I could say that the integral over all space, okay, of f of r, some function of r, Dirac delta function cubed of r minus a. So now we're shifted by an amount of a, d tau. We will use d tau as an elemental volume differential in this class. So this is equal to f of a. So it will pick up the value of a. Everywhere else it will be 0. Okay. Now, in the book, and the reason that this is important, because in the book, in one of the sections, right, you found that the divergence, I believe, the divergence of r over r squared, this turned out to be 0 everywhere except at the origin. So that's when r does not equal 0, right? Now, the puzzling result was the fact that the integral over any volume containing the origin turned out to be 4 pi. So how can you reconciliate those two results? That's for all r, including r equals 0. Well, this is exactly where the Dirac delta function comes in order to merge these two together, to tell you that the divergence of r over r squared, right, is actually equal to 4 pi times this. Okay. Second. You see? So what that means is when r equals 0, right, this guy becomes 1, and the answer is 4 pi. And when anything else other than 0, the answer will be 0. And so that's why one of the equations in chapter 1 that's really useful and will come in handy is that the divergence of any unit vector over that vector squared, right, is equal to 4 pi times the Dirac delta function of that vector pi. You see? So let's box this result because it's such an important result. And of course here, what this guy is signifying is, like we said earlier, is r minus r prime. It's the vector from the from the source to the field, the separation vector. This is the separation vector that we will use, separation vector. Okay, so the derivative here is with respect to r. R prime is held constant. Okay. So yeah. So okay. So back to the question on the test. I think this will be enough to answer the question. It said. So okay. So we briefly we did discuss what the Dirac delta function is, and so now the question becomes how to evaluate this. Yeah. So from minus infinity to plus infinity of x minus 6, Dirac delta function of x minus 6 dx. Okay, well, we said that this will be 0 everywhere except at 6. And this will pick up the value of the function. So this is f of x here. So this will be f of 6 and 0 everywhere else. And well, f of 6 is just f of 6 minus 6. I mean 6 minus 6. So this will be 0. So this is kind of the story with the Dirac delta function. Questions on the Dirac delta function? Now, the only thing that is left to be said is, if let me just mention these last two things here. You remember earlier we said that the divergence. So let me write this down. So the separation vector is just r minus r prime. And what's the divergence of 1 over the separation vector? Well, if you take the derivative of this with respect to x, y, z, you're going to get minus 1 over the separation vector squared multiplied by the separation vector itself. Okay. Right, when you do it. So now, if I were to do the Laplacian of this, if I were to repeat this one more time, you're going to get minus 4 pi times the Dirac delta function of pi at the separation vector. So so at 0, the answer will be minus 4 pi because this guy blows up. But anywhere other than 0, the answer, anywhere other than 0, the answer will be 0.
If it was in 3 dimensions, that would you get something? Would you be able to?
Yeah, this is yeah. Remember, this is in 3D because you know, the separation vector is hiding in it all the components, the x, y, and z. That's why how I got this unit vector here.
All right.
Some books like to use r minus r prime. They don't use this pi because it's not very illuminating. But generally speaking, it does just fine. Because usually, if you're dealing with a potato-shaped body, for example, okay, I didn't want that. Let's just say No, let me turn this off. So if you're dealing with a potato-shaped body, right? And let's say you take an elemental volume of this guy, like a piece, okay? And this piece, so let's say the origin is here. So let's say that from here to here is r prime. And let's say we want to calculate the field. Let me change the color here. Let's say I want to calculate the field here at this point.
Yeah.
Okay. And so this from here, so from say from here to there. Let me close this with a different color. Let's say this. Okay. So this is our R, and this is the separation vector from any point here, right, to where we're calculating the field, for example. So R prime plus the separation vector would get you the vector R, where that point is away from the elemental volume that we are picking. And of course, this will involve integrals because to capture the entire potato-shaped body, you need to integrate over the entire body.
All right.
Cool.
I think we can pick up tomorrow.
Yeah, that's fine. So any questions so far?
So far, I think I'm good.
Okay, good. So I'll see you tomorrow. Take care.